the NASA hangar at the Vandenberg Space Force Base on the central coast of California. I'm your host, Daryl Nail, and joining me is Kelly Fast. She is a program scientist with the Planetary Defense Coordination Office. Welcome, Kelly. It's great to have you here.
Thank you, Daryl. It's fabulous to be here helping to cheer DART off the planet.
Now, right at the top, let's talk about this. Are there any asteroids threatening Earth that we know of?
Now, thankfully, there are no known asteroid impact threats to Earth. You keep tracking them. We don't know of any. It's the one that we don't know about, that we're concerned about, but that's why NASA surveys for near-Earth asteroids, searches for them, and does a test like DART to have that in the toolbox.
Okay, and this asteroid DART is going to hit. What's the story there?
Well, the asteroid Didymos does not pose an impact threat to Earth. It keeps its distance, it gets no closer than 3.7 million miles to Earth's orbit, but that's what makes it a fabulous test situation for DART. We can go safely test an impact, the kinetic impact technique, and Didymos is the perfect laboratory for that.
Okay, and this spacecraft, is this something that could one day save the planet?
Well, what's nice about this, I mean, it's a nice mature technique, kinetic impact. You just impact something, but now we're actually going to test it. So this is going to be really good to have something in the toolbox that we've actually tried, taking it from modeling to an actual test.
Well, it is certainly exciting just to hear you talk about it. And when that moment happens in the fall of 2022, when that impact happens, that's going to be quite a moment.
It's going to be amazing.
All right, Kelly, thank you so much. And there's so much more to discuss about asteroids, planetary defense, and the DART mission. So let's get right into it with a quick breakdown of the DART spacecraft. DART has a mass of 670 kilograms, about a golf cart size or vending machine size machine. It uses hydrazine thrusters for propulsion and roll-out solar arrays for electric power. Now, DART has just one instrument on board, and there it is at the bottom. And that instrument is a Draco camera, which will feed images to an autonomous navigation system, steering it smack dab into an asteroid. Now, here's how DART got here. It was pulled by this semi-truck 2,900 miles across the country from the Applied Physics Lab in Maryland, all the way here to the Vandenberg Space Force Base. It took the team 46 hours to make the trip. You see that box right there? That's the protective container that was removed and is being stored here in the NASA hangar, while this DART spacecraft was carefully prepared for the launch and then put into that protective fairing. What a beautiful shot that is, Kelly. And then earlier this month, engineers mated the DART spacecraft inside its protective fairing to this SpaceX Falcon 9 rocket, which you see here, and DART's at the top of the rocket. It was then rolled out to the launch pad at Space Launch Complex 4 East, where it is now awaiting liftoff at 10:21 p.m. Pacific, 1:21 a.m. Eastern Time. Now, as we follow pre-launch operations, we also have some cool stuff to show you along the way. Our own Kelly Fast will give a fun demonstration. There she is. She's going to help us visualize a close approach asteroid, and she's moving quick. We'll also head into space where two astronauts will demonstrate in microgravity the kinetic impact technique that DART will be using. And also, this is kind of fun, we'll hear from a Hollywood director, Adam McKay, about his new science fiction comedy, Don't Look Up. It's about an Earth-ending comet that he'll compare with reality. But first, it's T-minus 45 minutes and counting. Let's get our first check on launch operations and introduce our launch commentators for today, NASA's Marie Lewis and Denton Gibson. Marie, preparations have been going on for many hours. Where do we stand right now?
Well, at the moment, Daryl, everything is still go for launch. We listened to polls just a few minutes ago internally with the spacecraft team and NASA engineering. No red flags, everything looking right on course. Want to introduce our commentator who's making his debut launch commentary tonight, Denton Gibson with the Launch Services Program. You're a mission manager, no stranger certainly to Falcon 9 and missions like this, but this is your first time in the commentary booth, so welcome.
Oh, thank you. Thank you. Thank you for having me. I'm excited to be here. It's launch day, so I'm looking forward to this.
And the teams on console have been going through their steps methodically since a little before 7 o'clock this evening Pacific time. There is a live view of the Falcon 9 rocket at Space Launch Complex 4E here at Vandenberg Space Force Base. And in less than a minute, we expect to hear the NASA launch manager, Omar Baez, poll the NASA team for launch readiness and readiness for propellant load to go ahead and proceed with that. If that is all go, that will begin at T-minus 35 minutes.
Right. And the reason why you hear this poll at this point in time, because there's so much going on much later in the process. So they try to have the poll early so that way the team can focus on the telemetry and focus on the data coming from the rocket and really pay attention to everything that's going on leading into those last few minutes.
And we're just standing by for that NASA launch manager poll.
This is Dan Lim on the NLMnet with our propellant loading poll, starting with NASA CE.
NASA CE is go.
SMA,
SMA is go.
SMD,
SMD is go.
NASA Mission Manager,
NASA MIM is go.
LSP.
LSP is go.
Team's ready to proceed in the cryo tank.
So what you just heard was the NASA launch manager polling the various NASA teams to make sure that they're ready to go to proceed with propellant loading and launch. And launching a rocket is very difficult because it takes multiple teams to do that. And that's the various teams that you heard the NASA launch manager polling to make sure that they're ready to proceed with the count.
One thing I want to point out as we look at the rocket live on the pad on an unusually clear night here at Vandenberg is the soot on the side of the rocket, and that is because this booster has already been flown twice, in fact, but this is the first time for a Launch Services Program mission.
That's correct. We've done a lot of work getting to this point where we've comfortable where we are with this, and we're looking forward to this launch. And we have a lot of familiarity with this booster because we actually launched this for the first time on Sentinel-6 almost a year ago today.
Yeah, so happy anniversary, Sentinel-6, and we're getting ready to fly this booster once again on SpaceX's first interplanetary mission. So really exciting stuff coming up. By the way, weather is 90% go, so things are looking really great here so far. Daryl and Kelly, for now, we'll send it back to you.
All right, thank you, Marie and Denton. And so that's a great report. They're fueling up the rocket. Kelly, it's getting kind of exciting.
I'm really relieved to hear that report that that it looks like things are going to go. And I think of the DART team. I mean, they've been working on this for years, but they've brought a spacecraft to the launch pad through a pandemic, and so they really need to be commended.
That's a great point, and you are right about that. Astronomers now all over the world, what's interesting to me about this is after this impact happens, they'll be able to see some kind of change?
Right, it's a unique mission in that there's an astronomical component to it. When DART impacts the moon of Dimorphos in fall of 2022, it will change the orbital period of that little moonlet. But from the Earth, it's just a point of light, but that point of light varies in brightness because that moonlet travels in front of and behind Didymos, and so that can be measured, and that rate of that light going up and down is what they're going to measure the change in that, and that's how we're going to see exactly what DART did to Dimorphos.
That's fascinating to me because it's literally just light you're looking at. We've never seen this little moonlet, but we see the light, and that's how we gauge it. More stuff to come from Kelly. Thank you very much. We are T-minus 41 minutes and counting. Here now is everything you need to know about the DART mission.
DART stands for the Double Asteroid Redirection Test, and the DART mission is to basically go hit an asteroid and see if we can move it. Earth is surrounded by small objects called near-Earth asteroids, and some of them are potentially hazardous. So planetary defense is cataloging, figuring out where all these objects are, but also trying to prevent them from hitting the Earth.
So far, we've only been able to predict the impact of 2 or 3 objects ahead of time. Those objects were small enough, they burned up in the atmosphere, and they were no danger to anyone. But what happens when an asteroid or any object is going to impact the Earth is that the Earth and that object want to be at the same place at the same time. We can't change the speed of the Earth, so the idea would be to change the speed of the impactor.
Now, we chose to do this demonstration at a binary asteroid. The main asteroid is called Didymos, and its moon. DART is actually targeted to the moon of the Didymos system. And that's a much smaller target than any spacecraft has ever managed to hit before.
This is the first mission to fly the next sea. There's the ROSA, the solar arrays, have an Italian CubeSat, but it's really all about smart navigation.
The DART starts out with the traditional mission design concepts where we use star trackers and optical navigation. This will be the first time that the spacecraft will autonomously guide to a target.
The narrow-angle camera will be used by the spacecraft to home in on the target and hit it, and then the CubeSat will fly past the target and it will return the data directly to Earth on its own.
The tough part about it is that we're guiding ourselves into the asteroid, we're taking pictures, and we're sending data back all at the same time. You know, Didymos is a system that is tightly locked together, so we're going to try to push on the little moon and try to push it away in such a way that it will change the orbit of the asteroid and it will move it.
Mostly what we're looking to do is change the speed of the incoming object by maybe a centimeter per second. So that's not very fast, but if you do it enough seconds in advance, you can cause it to miss the Earth entirely.
DART is actually the first planetary defense mission. This is a continuing series of missions for planetary defense. We had this unique opportunity to demonstrate the method and also to learn exactly what happens when you crash a spacecraft at high speed into an asteroid.
While the launch and spacecraft team are busy preparing for liftoff, the mission operations team located across the country in Laurel, Maryland, is preparing to communicate with the DART spacecraft after an hour-long flight on a Falcon 9. Let's bring in Samson Rainey now to find out what they're working on.
Hi, Daryl. I'm at the Johns Hopkins Applied Physics Laboratory, which has a number of historic milestones in space. We're talking about the first mission to orbit Mercury, the first flyby of Pluto, and of course, here we are with our next major milestone with DART. Right now, I'm standing outside of Missions Operations Control, which is essentially the nerve center for the spacecraft after launch. It controls everything from propulsion to the power supply. Let me give you a quick lay of the land here. If you look behind me in this corner, there is a U-shaped configuration. That's called the command pit, and it houses the flight controllers as well as the mission operations manager. Now, flanking the command pit on either side are the consoles for the subsystem experts. Right now, the team is basically looking at their consoles and making sure all systems are green or a go for launch. Now, it might seem like quite an uneventful scene in the back as you're seeing right now, but I spoke to Ray Harvey earlier. He's the mission operations manager, basically in charge of the overall health and functioning of the spacecraft. And he said that uneventful, or dare I say boring, is exactly what we're going for in this final countdown to launch. So there's a lot going on here, and what's going to happen is, what's cool about the spacecraft after launch is that there are a number of pre-programmed and automated sequences that will occur. So about an hour after launch, the spacecraft will separate from the launch vehicle. At this time, the spacecraft will be in a rapid rotation. So at that point, thrusters will engage and fire and bring that spacecraft into stabilization. They call that detumbling the spacecraft. Now, after the spacecraft is stabilized, the next part of the automated process happens, which is the unfurling of the ROSA solar arrays. Now remember, each array is 28 feet long, so it's going to be an intricate multi-step process to bring DART's wings to spread. And so that probably will take 2 hours alone for that process to happen. So after the spacecraft goes through those automated sequences successfully, the team will then take control of the spacecraft. Navigation systems will be engaged, and the team will then bring the DART spacecraft to a default orientation, which includes, most critically, making sure that those solar arrays are pointed toward the sun and gathering energy for the journey. So as you can see, a lot is going to happen tonight, and so the team expects a graveyard shift. But stay tuned, because later on in the show, we're going to come back and talk to some of the engineers and scientists and learn more about the mission. So stay tuned. Thanks, Daryl.
All right, time to turn our attention to a critical component in the pre-launch operation, and that's the weather. It was a beautiful day today on the central coast of California, and fortunately, we also have a beautiful launch weather forecast. So let's take a look at the satellite, and you can see the clear area as we shift from day into night. That's California in the center, of course, and that peninsula there, that's where we're launching the rocket. There are clouds to the north and to the west, but the area around the central part of the state where we are fairly clear with only some high cirrus clouds from a weak cold front that did move into the area and lowered the temperatures here. Now, the Space Launch Delta 30 launch weather officer, Max Rush, says that this will bring elevated winds both on the ground and in the upper atmosphere. So they are watching those closely, but overall, take a look at this launch day forecast. It is nearly perfect, 90% go. The wind is 18 miles per hour. That is the gust out of the north-northwest. Temperature down to 48 degrees, so it's a little chilly out there. The concerns are winds and offshore clouds, as you saw some of that cloud cover over the Pacific. Now, the Space Launch Delta 30 weather team will be monitoring all of those winds and conditions as we move forward. Now, the winds on the ground and the winds up in the upper levels of the atmosphere, this is always being monitored by the Space Launch Delta 30 team. And to do that, meteorologists will use a weather balloon. And they invited us to watch and participate in that release that helps inform that launch weather forecast you just saw.
Hey, Mike Schmeiser, Daryl, meteorologist of the Space Launch Delta 30. Good to see you again.
Good to see you.
So what do you do here?
This is the Nerve Center for Weather Forecasting. There's about 240 sites just like this across the United States. And every day, twice a day, all of those sites release a balloon. So we're putting out the data for not only National Weather Service, but also for our forecasters. Absolutely critical data. Can't do weather forecasting without it.
Once you get the data, then how do you look at it and study it?
So the data comes in 5,000-foot blocks. Each one of these dotted lines shows 5,000 feet. As it comes in, it takes about 5 minutes for that data to come in. And this is the wind speed and direction.
So I understand you're going to be releasing a balloon in just a few minutes?
Yeah, absolutely. In fact, I've talked to the guys out there, and they said you're good to go to be the guy to release it.
You're going to trust me with the weather balloon?
I trust colonels with weather balloons, so I'll trust you.
All right.
There you go, 10 seconds. I feel like the biggest hit of the park. Perfect. Interesting fact about that balloon you just released, when it gets up to 100,000 feet, it'll be about the size of a Greyhound bus.
That's incredible.
Yeah.
Wow. Well, Mike, thank you so much for having us out here. Really enjoyed it.
I'm really glad you came out. Thanks.
Took me back to being a kid and just releasing a balloon into the air. Thank you to the 30th for doing that. Now, most of the spacecraft NASA builds are intended to operate for many years or even decades, but not the DART spacecraft. It was built to be destroyed. So let's check in now with Raquel Villanueva, just about 5 miles away from us at a launch viewing location with more. And Raquel, looks like you got a little bit of a crowd behind you.
That's right, Daryl. There is a crowd of about a couple hundred people behind me getting ready and braving the chilly temperatures to watch this launch. And right next to me is DART Deputy Mechanical Engineer Lisa Wu to talk about how the spacecraft was built. Thank you so much for joining us today.
Of course. Thank you for having me.
So explain to us how DART was built and tested and designed.
That is a great question. So DART was built from the inside out. We started with components on the inside, including boxes such as our avionics that had the SmartNav system, our algorithm built by APL. Woo! That's basically what's going to autonomously take us to the asteroid. So once we tested everything on the inside, we closed up the box and we started doing everything on the outside. So we installed and integrated our solar arrays, our ROSAs, as you will roll out solar arrays. And then at that point, afterwards, we put on our NEXI engine, which you can see here in the video. That is our NEXI ion thruster, which is pretty cool. We closed up the spacecraft with blankets to keep the spacecraft nice and warm, and from there we had to take it through a series of very vigorous testing, including vibration testing and thermal vacuum chamber testing. All of this was really cool. One of our last things we installed was our Licha Cube from our Italian friends, and then we put it in our shipping container and shipped it from Maryland all the way out here to California. Right now it is on our rocket, and we are ready to launch.
And what was the biggest challenge the team faced when building the spacecraft?
You know, I think the biggest challenge that we faced was definitely having to build a spacecraft under the constraints of a pandemic. That was super difficult because building a spacecraft in itself is hard, but with pandemic and all the restrictions, it was really hard. But, you know, the team adapted. We did things very virtually. We did procedures online. We did shift work. And in the end, the awesome team we had made a spacecraft. So, hey, that's why we're here today.
Great. It's great to see you here now. And I'd just like to thank you for your time today, Lisa. And I will send it back to Daryl.
Kel and Lisa, thank you both so much. DART will take flight on a pre-flown SpaceX Falcon 9 rocket from Space Launch Complex 4 here at the Vandenberg Space Force Base. But once again, this pre-flown booster will make another return from space. For more on that, here's SpaceX engineer Jesse Anderson.
It was almost exactly a year ago when the Falcon 9 booster set to carry NASA's DART mission first took flight. On November 21st, 2020 at 9:17 a.m. Pacific time, Falcon 9 lifted off from Vandenberg Space Force Base here in California, carrying the Sentinel-6 Michael Frelich mission for NASA to its targeted orbit. Following that launch, the Falcon 9 booster returned to Earth for a land landing on the pad just adjacent to where it had lifted off from roughly 8 minutes earlier. This same booster recently flew a Starlink mission in May of this year from our Space Launch Complex 40 pad out in Cape Canaveral, Florida, landing back on our drone ship, Just Read the Instructions, in the Atlantic Ocean. Now today, this booster will make its third flight from the pad, where it all started with the launch of NASA's DART mission. Roughly 2.5 minutes after liftoff today, the Falcon 9 first and second stages will separate, and the second stage will ignite its single Merlin vacuum engine to carry the DART spacecraft to an interplanetary trajectory. The DART spacecraft will separate approximately 56 minutes into flight and spend the next 11 months cruising to its intended destination. Following stage separation, the first stage will make its way back to our autonomous spaceport drone ship called Of Course I Still Love You, which is currently stationed off the coast of California. Now keep in mind, it can be tricky to maintain the video feed as the booster makes its way back to Earth, but fingers crossed, we'll get some great views as it completes its third trip to space. That's it from us here in Hawthorne. Now back to you in Vandenberg.
All right, thank you very much, Jesse. And now time to check back in with the launch team at the Mission Directors Center to see how the countdown is progressing. Maria and Denton, that booster looks very familiar. I was out here a year ago, and it looks great on the pad, though you can tell it's been to space.
Yeah, you sure can, and that's what we like to see. You know, the reuse is so exciting. And Denton, I know you talked about this already, being a first for the launch services program, but you really were able to get a lot of insight from the reuse that you saw with cargo missions and the commercial crew missions for NASA. And so you're just building upon that. And it's really great to see. There's a live look again at the pad. And now we can see the liquid oxygen venting off the side of the Falcon 9 rocket. Fueling began about 9 minutes ago. And so the count has been really quiet these last few minutes, and that's a good thing.
Yeah, absolutely. I mean, that's what you want. You want an uneventful count. That means everything is going well. We're moving along in the count, progressing, and being where actually we're supposed to be at this point in time. So that's what we want to hear.
And liftoff is scheduled for 10:21 and 2 seconds p.m. Pacific time. So if you are watching from the East Coast, it's going to be already early the next morning. And there's a special reason why SpaceX fuels this close to liftoff.
Yeah, and that's because they use densified propellants, which are very, very cold. And so they fuel this close because they don't want it to warm up too much, and you want to keep it down in those really cold cryogenic temperatures prior to liftoff. And SpaceX has gotten very good at that, at fueling this late in the game. They're very efficient at it, and it's just a normal part of the process at this point.
All right, so we're going to continue to keep an ear on things. Next thing we'll be listening for is the SpaceX launch conductor poll at T-minus 4 minutes. That's the next milestone you see on that progress bar on the bottom of your screen. So we'll be listening in for that. And for now, we're going to toss it back over to Daryl and Kelly.
All right, thank you very much, Marie and Denton. And now we want to get back to the science of this mission and talk a little bit about the what if, Kelly. You know, This is a big deal. A lot of people probably haven't heard of this, like, oh, wait a second, should I be worried about asteroids now? But it really comes down to all the documenting and cataloging that you guys are doing. So how many asteroids are out there?
Right, well, NASA-funded telescopes are responsible for most of the near-Earth asteroid discoveries, which now number 27,532, according to the Center for Near-Earth Object Studies website.
Okay, well, and that's an up-to-date number.
It is.
So what about the asteroids that we don't know about?
Well, that's the thing of the subset that are of a larger size that could really do damage that the Earth's atmosphere doesn't protect us from. That larger population, we've probably only found about 40% of those.
Only 40%, which means there's a lot more out there.
So we keep searching.
Okay, well, we keep our eyes to the skies and eventually get a telescope up there, right, to look at this?
Right. NASA funds these ground-based telescopes that search for near-Earth asteroids, and they're doing a fabulous job, but it is also developing the Near-Earth Object Surveyor mission, which will be a space-based infrared telescope really designed to do this type of survey work and accelerate the rate of discoveries of near-Earth asteroids.
Great. Space-based telescope specifically purposed for looking for asteroids.
Right.
Looking forward to that mission. And so what if there wasn't enough time, though, to knock it off course? Well, earlier, NASA's Raquel Villanueva talked to two key people about how FEMA and NASA are working together on this.
While there's currently no threat of an asteroid or comet heading toward Earth, there is plenty of work being done to prepare for a potential threat. I'm here today with NASA Planetary Defense Officer Lindley Johnson and Leviticus Lewis with FEMA to talk about some of the measures being taken. Leviticus, Lindley, thank you for joining us today.
Glad to be here. Yeah, you're welcome.
Now, how do your agencies work together when it comes to planetary defense?
Well, we at NASA are tasked with trying to find any impact threat that might be out there, any asteroid or comet that is close enough to Earth that it could impact us, and then be able to determine when and where that impact might occur so that we can inform the emergency response community if we don't have enough time to do something about it in space.
FEMA is the Federal Interagency Coordinator and also an all-hazards organization. So planetary defense is just one more thing on our list of hazards that we should be prepared for.
One of the many emergencies. Now, Lindley, if there were to be an asteroid that posed a threat to Earth, what is being done to discover and track this?
Well, NASA and the Planetary Defense Coordination Office sponsors projects around the country at observatories and university space institutes that are searching the skies every night to find any asteroid or comet that could be an impact threat to the Earth in the future. We want to find them far enough in the future that we have a chance to do something about them, like use DART to deflect them off of that impact trajectory. But if the time is short and we're not able to do that, then an asteroid impact is just like any other natural disaster. And so the emergency response community needs to know when and where and what the effects could be.
And if an asteroid posed a significant threat, what steps would be taken next?
Well, we collect as much information as we can about the asteroid through the remote observing and determining the composition and size. It might be small enough that Earth's atmosphere would disintegrate it, but if not, then there could be damage at the surface. We want to be able to appraise the emergency response community how extensive those effects might be, what kind of area might be impacted by this natural disaster.
And Leviticus, how would FEMA work with NASA if this type of scenario were to happen?
So we're not going to be changing our procedures exactly, but we want to make sure we account for the differences in the science and in this particular scenario. So it'll be another emergency added to the list of things we handle every day.
Leviticus, Lindy, thank you so much for your time.
You're quite welcome.
You're welcome.
All right, DART is the first time we've ever used a spacecraft as a kinetic impactor into an asteroid. So we asked the astronauts on board the space station to demonstrate what a kinetic impact looks like in space.
Hi everyone, I'm Thomas Pesquet and I'm with my favorite astronaut Shane Kimbrough up here on the space station. Today we're going to talk about a very cool new NASA mission. It's called DART. Can you tell us and tell me a little bit more about what is NASA's DART mission?
Okay, yeah, so DART is NASA's first planetary defense test. So we're gonna try to do something we've never done before with the spacecraft. And now the purpose of this spacecraft and this mission, it has one purpose, and that's to crash itself into an asteroid and try to redirect it or try to move it into a different orbit.
So today, Shane, we're gonna demonstrate some of those principles that you laid out before. But can you tell us exactly how we're gonna do that?
We're going to try to demonstrate this asteroid kinetic deflection method, which is really the moment that spacecraft crashes into the asteroid. So here we go.
Shane is going to be the asteroid, and I'm going to be the NASA DART mission. I'm going to try to throw this CTB, and we'll look at the effect of that mass coming at him and the kinetic energy transfer. Shane will be perfectly stable. You ready? All right, here it comes. I've redirected Shane successfully. Pretty good. A while ago, we got out the door and we got some new solar arrays here on the space station.
And so the same technology we have here now on the space station is going to be used to power the DART mission on its way to this asteroid.
ROSA, in case you didn't know, but you knew, it stands for ISS Rollout Solar Arrays.
So we got a chance to go outside and install the very first two of these new IROSAs, or Rollout Solar Arrays, on the very end of the space station, out on the port side. These are different because, for one, they're much lighter and smaller. To me, they look very fragile when we were picking them up and moving them, but they're rolled up. So when they launch, they're kind of rolled up into a compact cylinder, which is great for launch conditions. And then once they get up on the space station or in space for a satellite or something, they can then roll these things out to be useful. And so the same technology we have here now on the space station is going to be used to power the DART mission on its way to crashing into an asteroid.
So that was pretty fun early in the piece, watching Shane get knocked into the side of the International Space Station. But is that how kinetic impact will work on an asteroid that's in orbit?
Well, the nice thing is the laws of physics are the same in deep space as they are on the International Space Station. The asteroid Dimorphos might react a little differently from astronaut Shane because in addition to being impacted by something, there might be material thrown off from the surface that will affect that motion too. So it'll be a little different, but again, it's all physics.
I love it. Okay. Well, a lot of careful consideration went into choosing the right asteroid to test the effectiveness of a kinetic impact with the DART spacecraft. So let's go back to the Spacecraft Mission Operations Center in Maryland, where Samson Rainey is with one of the scientists who helped choose the asteroid. But first, Samson has the latest from the DART spacecraft team as they prepare for launch.
Hi, Daryl. Welcome back to the mock. So right now the team continues to simply monitor all their subsystems to make sure they are continue to be a go for launch. And as you remember what I said earlier about uneventful equaling good, well, that's exactly what we want to continue in its final countdown to launch. But of course, we're only seeing the tail end of what has been a lot of work to get to this point tonight. Throughout the year, the team here has been rehearsing for what are called anomalies, which are instances where a problem arises. So say a ground-based antenna goes down. Well, the team has spent a lot of time flexing its responsive muscles to that and other scenarios. These rehearsals were happening as recently as a few days ago to give the team an upper hand to tackle any challenges that may come its way. So I just wanted to pay homage to all the engineers and technical experts that have been working hard to get us to the main event, which we all know is Impact with Dimorphos. That said, I want to switch gears a little bit and talk about the science behind the mission. And here to talk with me is probably the best person for the job is Andy Cheng, which is DART's investigation team lead. Andy, why don't you tell us about our target asteroid and why we chose it?
Yes, DART is the double asteroid redirection test. And it's a test of a kinetic impactor, a double asteroid that looks like this model. And what it is, it's two asteroids in orbit around each other. And DART will come and hit the moon of this system and change the orbit of the moon around its primary. And it will do that because we can measure the change in this orbit with ground-based telescopes. And that works like as follows. When the two during the course of the orbit, the two objects move in front of and behind each other, and each time that happens, the amount of light that you see from the system makes a dip. And so we time these dips in the light very precisely to measure the orbit period.
Great. Well, thanks, Andy. I heard you dreamt this up in your basement. And, 2 weeks ago, I conquered a video game, and I feel like we're on, equal footing now. So what do you think about that?
Well, I don't know how it feels to conquer a video game. I've rarely been able to do that.
Well, I can guarantee that it's not as big as, thinking of this mission. So
yes.
Back to you, Daryl. Thanks.
All right, thank you both. DART is one of a handful of asteroid missions launching this year and next to explore asteroids. Let's go back to our launch viewing location and join Raquel Villanueva, who is with a special guest. And I guess the crowds out there have grown a little bit, Raquel?
Yeah, that's right, Daryl. The crowd is growing, and you can hear the excitement building behind me as they get ready for launch. And joining me now is NASA Science Associate Administrator Thomas Zurbuchen to talk about what DART means to the agency. Thank you so much for joining us today, Thomas.
Good to be here, Raquel. Good to be here.
Exciting. Now, can you tell us about DART as NASA's first planetary defense test mission and how this mission will change how we explore space?
So first of all, everybody should be sure to know that this is not the first, not only the first and only mission, but really the first of many missions that we're going to do in planet defense. The second one we're already working on, which is to find the other 60% of threatening bodies. What's also exciting, though, is that this mission carries technologies we're going to use for exploration of the outer solar system, perhaps sample returns to comets, asteroids, or visiting the moons out there, the amazing worlds that are there.
And that kind of brings me to my second question. How is DART different from other NASA asteroid missions like Lucy or OSIRIS-REx?
So first and foremost, we're not crashing those at all, and certainly not intentionally, and actually no chance of that. Look, the other asteroid missions are all about learning from these asteroids about our history, the history of the solar system. These primordial bodies out there tell us about the building blocks of the solar system, and we still have a lot to learn. So asteroids are really exciting. They tell us a part of our own history.
And after DART launches, what other missions are you looking forward to in the future?
Wow, before the end of the year, we have 2 astrophysics missions. A small one focused on X-rays, the violent universe, kind of black holes and exploding stars. And then the biggest mission we've ever done, the James Webb Space Telescope, mission in the making for 20 plus years and part of dreams of thousands, if not 10,000s of astrophysicists worldwide. That's still before the end of the year, and many more next year.
It's a busy end of year ahead. Thank you so much for joining us, Thomas.
Thanks to you.
Back to you, Daryl.
All right, thank you both for that. And back inside the NASA hangar here. But by the way, that's the little box that DART came in. I just want to point that out back there. Isn't that great?
That's awesome.
I mean, this is where we keep the box for DART. But we don't want DART to come back into the box.
No.
We want to go to space. Hey, talking about your office, the Planetary Defense Coordination Office, you got the little patch there. In fact, I was observing a little Latin phrase that at the bottom. What does that say?
Hic servari diem, which means here to save the day. So.
Here to save the day. How about that?
Right.
What is the team doing to save the day?
Well, I manage the Near Earth Object Observations Program, which is involved, which funds projects to find and track and characterize near-Earth asteroids. So like at the University of Hawaii, the Pan-STARRS and ATLAS surveys and management of NASA's Infrared Telescope facility, or at the University of Arizona, the Catalina Sky Survey and SpaceWatch. And SpaceWatch actually discovered Didymos, the target of the DART mission. The Center for Near-Earth Object Studies, I know we're going to have a video from Ryan Park about calculating the orbits based on those observations and from observations around the world, because if you don't find the asteroids and you don't find out where they're going to be in the future by calculating their orbits, then you can't have a mission like DART. You have to know where the asteroids are.
And so for people to understand the difference, I hear this a lot, okay, what are asteroids and how are they different from comets and meteors?
Well, and again, that's something, maybe Ryan can tell us about that if we have the video, but...
Well, we don't have the video at the moment. We only have you.
Oh, darn. Okay, well then I guess I'll have to do that. So asteroids are the objects in space. Anything like larger than a meter in size, rocky object, that's an asteroid. Smaller, they're meteoroids, but those are asteroids in space. When asteroids or meteoroids enter Earth's atmosphere, and you see that streak of light as it heats up in the atmosphere there. That phenomenon, that visual phenomenon, is called a meteor. And then the pieces that survive to the surface, those are meteorites that you can go and pick up and then go study in the lab.
That was like the one in Russia. That was a
yes, exactly. Some meteorites left over. And then comets are the icy bodies in the solar system, creating those tails as opposed to the asteroids.
Okay. Thank you for breaking that down. We appreciate it, Kelly. And of course, folks, stay tuned after liftoff for an entire hour-long show. We're going to break down the DART mission from A to Z, as well as the spacecraft. And then Kelly will also help us understand what a close approach asteroid is, if you kind of have heard reports about it. She really gives a great visual. We'll check that out in a little bit. And we'll find out what other missions are being planned for other countries to protect this planet. Until then, let's join our commentators, Marie Lewis and Den Gibson, inside the Mission Director Center to take us through liftoff.
All right, thank you, Daryl. It is now at T-minus 8 minutes, 12 seconds and counting. There is a live look at Space Launch Complex 4 East at Vandenberg Space Force Base on the central coast of California. We can see white clouds billowing around the Falcon 9 rocket, standing 230 feet tall at the launch pad. The fairing holding the DART spacecraft another 43 feet. On top of that, the DART spacecraft, only the size of a vending machine, tucked safely inside that fairing. And that venting going on is normal venting of liquid oxygen off the side of the rocket as we are well into the fueling process and just T-minus 7 minutes, 30 seconds away from liftoff of NASA's very first planetary defense test.
Yes. And some of the cloud you see coming off of the vehicle there is because the liquid oxygen in the tanks are just so cold. So it's really, the air is really condensing around it, and that's what you're seeing, some of that vapor there coming off of the vehicle. And coming up very shortly, we will be hearing the call up for stage 1 engine chill has started. And basically what that is, it's basically getting the engines ready for engine start. It's going to reduce some of the thermal stress on the engines, and that's really what's happening there. And that should be coming up shortly here in a few minutes. And we just heard that call up for engine chill. It just started. And the next event that'll be coming up will be the stage 1 RP1 load complete. And that's basically they're just topping off the fuel tank on the first stage of the vehicle.
Shortly after that, the DART spacecraft will transition to internal power. That happens right around T-minus 5 minutes. And liftoff time tonight is at 10:21 and 2 seconds Pacific time.
And we're still progressing towards T0. The count is going well so far. Everything is progressing well. And at this stage in the game, soon, coming up soon, the other thing you will start to hear discussion about the strongback. And basically what the strongback is that fixture you see on the side of the Falcon 9 there. That is basically supporting the Falcon 9 leading into launch. It provides the power, the electrical power, and the fluids going to the Falcon 9 while it's standing there on the pad. And we should be hearing.
Spacecraft is on internal power.
We just heard a call out for spacecraft on internal power.
It's good news, exactly what we want to hear. Our view a little bit obstructed right now by the venting off the side of the rocket. And that structure you see just to the right is the transporter erector. And that is the strongback. It's hard to see behind the venting, but there are a couple of arms kind of clamped around the top of the second stage of Falcon 9 that will be opening shortly as that strongback begins to recline just a couple of degrees in preparation for liftoff.
Yeah, and one of the callouts you may have heard is the tanks are pressurizing for strongback retract, and that's really just they're pressurizing the tanks to make sure the vehicle is structurally sound so they can remove that support from the Falcon 9. And it may be a little bit difficult to see the retraction here because of the fog that's around the vehicle right now.
NLM, LD on countdown 1.
LD, this is NLM.
Looking to confirm you and your team are go for launch.
Yeah, NASA's go for launch.
All right, so we just heard that confirmation that the NASA team is go for launch. And we can see that strongback retract happening as we speak.
Yeah, and basically that was the last confirmation from between the NASA team and the SpaceX team to say that we're good to go. And
so, go ahead.
And next milestone you hear coming up would be the stage 1 LOX load complete, and that's basically topping off the oxidizer tank on the stage 1. And that should be coming up here shortly.
And you can see a little bit better on your screen now that the
stage 1 LOX load complete.
Yep, just heard that confirmation. So the stage 1 is completely topped off of fuel and oxidizer, so we're looking good on stage 1 right now. And shortly coming up, you'll hear them topping off the stage 2 tank.
There's a wider view now of the transporter erector. You can see that recline. And as we get into those final seconds before liftoff, we will see that recline even further, all the way to 45 degrees just before liftoff, clearing the way for DART to take flight.
Yeah, and as you see, the strongback is tilted back a little bit. You see some cables that are still connected to the Falcon 9. Those are the umbilicals that are still providing power and fluids to the Falcon 9. And at liftoff, they will disconnect, and the strongback will move even further out of the way and to give it a nice clearance when it takes off.
We'll have a series of rapid events after liftoff that will guide you through with that progress bar. And Falcon 9 will have 2 burns for this mission.
Stage 2 LOX load complete.
We just got that confirmation of stage 2 LOX load complete. At this point in time, all of the propellants have been loaded onto the launch vehicle, and everything's looking good.
And in the meantime, the SpaceX drone ship, Of Course I Still Love You, is standing by in the Pacific Ocean, ready to receive the first stage booster that will be landing a little more than 9 minutes after liftoff on the drone ship. We don't expect to hear sonic booms here on land because it's coming down in the Pacific Ocean. So if you were here for Sentinel-6, you probably heard those a couple of sonic booms. That was because the booster was landing on land. Not the case this time.
Yeah, it would be awesome to hear it though. It's
Falcon 9's in startup.
It's awesome to see. We just heard a call out that this Falcon 9's in startup. That means it's going through its startup sequences. The flight computer is taken over and it's going through its process.
Falcon 9, DART, go for launch.
And we just heard that final call that Falcon 9 and DART are go for launch. T-minus 35 seconds and counting.
T-minus 30 seconds.
T-minus 20 seconds.
T-minus 15. 10.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
So we're getting a nice view of the onboard cameras from the Falcon 9. So you can see it looking towards the aft end of the first stage, and you can see those engines coming to life.
Stage 1 chamber pressure is nominal.
And Falcon 9 will be reaching max Q in just seconds, the moment of peak mechanical stress on the rocket.
And here in the Mission Data Center, we can feel the rumble from the Falcon 9, and it's always amazing to hear and feel.
Power and telemetry nominal.
Everything looking good right now. It's really shaking the building where we are.
Vehicle supersonic.
Just heard that call out for supersonic. Going faster than the speed of sound.
Max Q.
And we've just passed max Q, that moment of peak mechanical stress on Falcon 9.
And everything's looking good. We're still getting some nice views of the onboard Falcon 9 camera. And we should be coming up on main engine shut off here in about a minute. So far, everything's looking good. All reports are nominal.
INVEC chill has started.
We just heard the call off INVEC chill, so that's where it's getting ready to prepare the second stage for engine ignition.
Now that main engine cutoff, or MECO, we expect at T plus 2 minutes 30 seconds, and then almost immediately after that, the first and second stage of Falcon 9 will separate, followed by the stage 2 first ignition, and then shortly thereafter, the jettison fairing at about T plus 3 minutes 8 seconds. So far, nominal liftoff.
And as if you notice, the plume or the flame coming from the engines have gotten bigger. That means it's high in the atmosphere, where the atmosphere isn't compressing the flames coming from the launch vehicle.
MECO.
Okay, we just heard
Stage
that.
separation confirmed.
INVEC ignition.
So we just got confirmation of MECO, stage separation, and stage 2 ignition.
And so this is a view of the stage 1 Falcon 9 booster. You can see those hypersonic grid fins beginning to extend. The shot is a little bit dark, but you can see them extended out from the base
Bearing separation confirmed.
of the booster. And we just heard confirmation that the jettison fairing is complete. And those hypersonic grid fins help guide the Falcon 9 booster back down towards Earth. Again, it's heading towards the Of Course I Still Love You drone ship.
Stage 2 on nominal trajectory.
So we just heard everything's looking good for stage 2. You heard the positive confirmation of fairing jettison. And the Falcon 9 booster will be coming back. They'll be doing 2 burns. They'll be doing a boost back burn to get it closer to the Of Course I Still Love You, that's sitting about 400 miles south of where we are, off the coast of Baja, California. And then they'll do another burn for when it's coming in for a landing.
We're at T plus 4 minutes 6 seconds, and so far nominal ascent of the DART mission, NASA's first planetary defense test. Falcon 9 booster will begin its re-entry burn in a little over 3 minutes.
So far, everything's looking great. And that's exactly what we wanted to hear. It was awesome to hear it and feel a launch while we're sitting here in the Mission Data Center.
Yeah, that rumble never gets old.
Yeah.
And hard to believe in about 11 months from now that that DART spacecraft the size of a vending machine is going to
Mid-flight guidance.
crash head-on into Dimorphos at the speed of 15,000 miles per hour.
Yeah. And as we were talking about before, how fast is 15,000 miles an hour? I mean, it's like going from New York City to Los Angeles in less than a blink of an eye. So faster than you could blink, you travel across the country. So right now we're getting a good video that's looking at the interstage.
We're obviously having some technical issues with some of our video feeds.
Stage 2 on nominal trajectory.
Trying to get those feeds, get those kinks worked out so we can get those views back for you. But in the meantime, we will continue to talk you through everything that we're hearing. We can't see those views, but we are hearing that everything is nominal and on track.
Yeah. And as as you heard before, it may be difficult sometimes to get the video from the stage 1 landing. It's coming in very fast, and sometimes it's hard to get that video.
Yeah, that's a great point. Okay, we can see, and we see a view there. It's just very dark out.
Okay, so look like we're getting some good video.
Stage 1, FTS is safe.
Stage 1, entry burn startup.
All right. All right, so we got stage 1 coming in.
Now you've got a better look at those grid fins.
It's always amazing to see stage 1 coming back in for a landing.
Stage 1, entry burn shutdown.
All right. So
Okay, we've got a beautiful shot of stage 2 now.
Stage 2, FTS is safe.
Terminal guidance.
what we're looking at is the nozzle of stage 2, and you see it glowing hot.
Loss of signal, Cook.
At this point in time, everything's looking nominal.
And what you're seeing is that MVAC engine on the Falcon 9 second stage glowing, glowing red hot. And we just heard that engine shut down.
So stage 2 just completed its first burn of the first of 2 burns. So the first burn of second stage is helping to circularize the orbit after it's the launch vehicle has gotten off of
Stage 1, landing burn.
the surface of the Earth. And then there's a second burn that'll be coming up. But right now, we are getting the landing burn from stage 1. It's coming in for his landing. Looks like we're getting some good video.
Stage 1, landing leg deploy.
You can see the drone ship. The landing legs are out. All right, so we're back. We're getting another view of stage 2 during its coast. And we just heard positive confirmation of stage 1 landing.
Yeah, it's tricky to maintain that feed from the drone ship at the moment of landing, but we do have confirmation that the first stage booster has landed safely and successfully on the Of Course I Still Love You off the coast of Baja, California. And so now we are in the first coast phase of the Falcon 9 second stage, of course, still attached to the DART spacecraft. So it's going to be coasting for the next 20 minutes or so, give or take, and then second burn will get started. So we're going to keep an ear on things. But for now, we want to learn a little bit more about DART's mission. And to kick us off, we want to hear from the director of a new Hollywood movie about a cataclysmic comet.
I heard there's an asteroid. Tell me about it.
Hi, I'm Adam McKay, director of Don't Look Up. Our movie is about 3 scientists who tried desperately to warn the planet of an impending doomsday comet and are ignored. Our movie's made up. It's a comedy. But in fact, the brilliant scientists at NASA are actually launching a mission. It's called DART, the Double Asteroid Redirection Test. And what they're going to test is, can you send up a mission that can deflect an asteroid and steer it away from Earth if, God forbid, something like that were ever to happen? Remember to keep an eye out for it. It's going to be spectacular.
Thanks to Adam McKay of the soon-to-be-released science fiction comedy Don't Look Up. Folks, we are back inside the NASA hangar, and though the movie is not real, the Double Asteroid Redirection Test, or DART, is real, and we are ready to show you every aspect of this mission with the experts who know. So welcome back, everyone. I'm Daryl Nail, and with me is Kelly Fast, program scientist with the Planetary Defense Coordination Office. We hope you really enjoyed watching the launch. I know Kelly did, because as it was going up, you were going, go, go, pumping your fists.
That was so exciting to hear the rumble of the rocket noise come through the hangar here, but then just, again, being so excited for the team that has worked so hard on this. I know they are partying it up wherever they're watching from, and so I'm so excited for them.
Yes, especially that launch viewing location out there. I heard that it was a fantastic view, and that was pretty neat to see at least the first part of the landing where it was coming down and illuminated the ship. But even more so to see that DART spacecraft and the fairing come out. There it is, going to space.
Oh, I know we're not out of the woods yet. We still got to get that all the way out to Dimorphos, but this is a huge step along the way.
Absolutely. That is very important, because there is a lot more work to do to get this. And of course, we're going to be tracking all of that. You know, going back to that movie trailer, you know, Hollywood's always had fun with asteroids and, you know, ending the Earth with one of them. But the movie's called Don't Look Up, but really, you're kind of evidence that we're looking up more now than ever.
I like that Adam McKay kind of put it into context, that it's fiction, it's a comedy, but you know, in the real world, there's a lot of work going on with a lot of scientists looking for near-Earth asteroids, getting them cataloged. There's an international asteroid warning network. There's astronomers around the world doing this, and it's a big focus at NASA. And so it's the only natural disaster that we could prevent, an asteroid impact. And so why not use your capabilities to look, you know, to the extent that you can, rack those up, and then do something like DART, so that you've got a tool in the toolbox there.
Absolutely. And there's so much more to talk about. You know, there are other ways, I've heard, that we could do this. This is one we're testing. We'll talk to Lori Glaze about that. And then we'll also have your close approach demonstration, which we're really looking forward to. So that's coming up in just a bit. So in the next hour, we are going to tell you everything you ever wanted to know about asteroids and break down the DART mission from A to Z. And we're going to start with an overview of this mission.
In case there was an asteroid coming towards Earth and you're there, you can actually stop it. I mean, that's kind of fantastic.
NASA is crashing a spacecraft into an asteroid.
What? You think science fiction, but this is real. Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen.
I'm Lena Adams. My name is Kelly Fast.
I'm Andy Rifkin.
I'm Justina Sorovitz, and I help tell the story of the DART mission.
I'm a planetary defender.
And I study how the orbits of asteroids change after we hit them with spacecraft.
My job was primarily to make sure that all the systems on the spacecraft work together.
The DART mission is NASA's first test of a planetary defense technique called kinetic impactor.
DART is the double asteroid redirection test.
It's just a spacecraft that is going to go and smack an asteroid.
The moonlet Dimorphos, which orbits the asteroid Didymos,
And see if we can change its trajectory just a little bit.
in order to show that we can deflect incoming asteroids if we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount.
But in space, just a little bit is just enough to make an asteroid actually miss us.
In the event that an asteroid is discovered well ahead of time before it might impact Earth.
Behind me, you see the spacecraft.
It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are going to go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar array opens out, it's going to swing out in this direction. The asteroid's only 2 football fields in size.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
You can see Didymos and Dimorphos as 1 point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
We're super excited and nervous as well.
I feel really honored and humbled to be working in an area of science that has such a broader impact, figuratively and literally.
No DART! The dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are, we can actually do something about it. I think this is just wonderful.
And as was mentioned in there, this is the first planetary defense mission. And this is your office we're talking about, Kelly. So for the audience out there that doesn't understand or hasn't heard of this before, what is the Planetary Defense Coordination Office? What do you do?
Well, right. Well, NASA's actually been working on near-Earth asteroid research since 1998, so this has been going on a long time. But in 2016, it was really formalized more in the creation of this Planetary Defense Coordination Office, which is in the Planetary Science Division at NASA headquarters. And it takes that legacy near-Earth object observations program, all the, the finding them part of the program, and then combines that with these other activities like DART, like the development of the Near-Earth Object Surveyor Space Telescope, like our interagency collaborations like we saw with FEMA there, our international collaborations, and formalizing all of that and leading the Planetary Defense Coordination Office. Lindley Johnson, we say he's got the coolest title in the solar system as NASA's Planetary Defense Officer.
All right, and he sure does. I enjoy listening to him in that interview earlier. Now, throughout the show, we will be taking the most popular questions NASA gets about asteroids and posing them to experts like Kelly. This next question is for NASA expert Marina Brozovic. When was the last time an asteroid hit Earth?
Well, the answer depends on whether you're asking about small or large impacts, because Earth gets hit all the time. But luckily for us, the vast majority of these impactors are small, and they just burn in the atmosphere. The most significant fireball event in over 100 years occurred over Russia in 2013. We actually got hit by an asteroid that was the size of a small building, and that one disintegrated about 20 kilometers above the city of Chelyabinsk. And it deposited a fair number of meteorites on the ground. And I happen to have a piece of that Chelyabinsk impactor right here in my hand. But what about big impacts? The ones that leave craters tens of kilometers wide and cause huge amount of devastation. We have to go far back in time for such an event. And those old craters are not easy to spot, because by now they're heavily eroded, they're filled with sediment, or they can be at the bottom of the ocean. But to keep the long story short, small impacts, they happen all the time, especially given that about 15,000 tons of space dust hit Earth every year. And large impacts are rare, and we're talking millions of years rare. So when was the last time an asteroid hit Earth? Probably today, but the odds are it was very small and just burned in the atmosphere.
The binary asteroid system DART is taking aim at was chosen for many reasons. Let's join Raquel Villanueva with a special guest to explain that. But first, Raquel, you saw the launch in person live. What was that like?
Ooh, it was chilly with lots of excitement and lots of cheers, lots of fun. And I am here with DART program scientist Tom Statler to talk about the double asteroid mission. Like, what did you think of launch, Tom?
Oh, Raquel, it was a beautiful, beautiful launch and tremendously exciting.
Now, can you tell me why the asteroid was chosen?
Oh, well, a binary asteroid system and the Didymos binary asteroid system is the perfect natural laboratory for the double asteroid redirection test. For one thing, the larger asteroid makes sure that the smaller asteroid is held in orbit around it, so there's absolutely nothing that we can do that would make this asteroid a danger to the Earth. But more important, it's about the measurement. We need to be able to measure how efficiently DART deflects the asteroid, and we're using that binary orbit of the little asteroid around the big one to do that. We're going to change the period of that orbit by just a few minutes, and we're going to be able to measure the size of that change using telescopes on Earth in the weeks and months after impact and precisely determine exactly what it was we did.
Now, DART is called a kinetic impactor, which is intended to change the orbit of an asteroid. So what kind of mass and speed is needed to alter the orbit of this particular asteroid?
Well, the DART spacecraft weighs about 500 kilograms, which Andy Rivkin, one of the investigation team leads, said the other day is about the mass of a small cow, which is, I guess, true. And it's going to be impacting the asteroid at a speed of about 15,000 miles an hour. So at that speed, it covers the last 4 miles to impact in 1 second. Now, that's going to deliver enough of a push to the asteroid to change its motion by a fraction of a millimeter per second. But it is more than just the push of the spacecraft. It's also the energy released in that tremendous collision at 15,000 miles an hour.
Now we can envision the small cow. Now, really quickly, how do you measure success for this mission?
Well, success is, of course, first, we want to execute the kinetic impact and strike the asteroid. But success is really being able to see the magnitude of that change. And at the end, when the observations are done a few months after impact, having that measurement and knowing exactly how efficiently we deflected the asteroid, and then later with additional data being able to put that in context and knowing what we might have to do for a similar asteroid or a different asteroid in the future if we ever do need to deflect one.
Tom, thank you so much for answering our questions today.
My pleasure, Raquel.
I'll send it back to Daryl.
Thank you, Raquel and Tom. And so now I have a clear picture of the size: vending machine, golf cart, and cow. That's great. Crystal clear now.